And a proof has been announced of a unsolved so far conjecture called the ABC conjecture. If this proof is right, then it's going to be news on the scale of Fermat's last theorem was in the 90s, which was this big unsolved problem, and it was this huge event. So it's really exciting. We don't know if this proof is right yet, so a Japanese mathematician called Mochizuki has released these papers, and altogether it's 500 pages long. He's been working on this for a very long time. He's come up with his own theory of maths, a whole new body of maths, and he's called it inter-universal geometry. I know nothing about that, very few people do. Even the experts don't know much about this at the moment, so it's going to take a very long time to make sure if the proof is right, because they're going to have to learn this whole new theory of mathematics. So the ABC conjecture involves the most simple formula you can think of. It's this: A plus B equals C. Doesn't get much easier than that, and that's where it gets its name from. The rules are, these are whole numbers, and they don't share any factors. So that means if I can divide A by 2, then I'm not allowed to divide B by 2. Or if I could divide A by 3, then B is not allowed to be divisible by 3. They're not allowed to share any factors like that. All right, let's try an example that works. 1024 plus 81 equals 1105. Right, now let's just check they don't share any factors. In fact, I picked these on purpose. This one is 2 to the power 10, and this one is 3 to the power 4. So they don't share any factors there. Oh, and this one, I'll do the same, is 5 times 13 times 17. Now, this is what I want you to notice. On the left-hand side, we've got lots of prime numbers. We've got 10 of them over here and another 4, loads of them over here. On the right-hand side, you only have 3. And this is what you tend to see most of the time. This is what's normal. If you get lots of primes on the left, you only get a few on the right-hand side. So this is what the conjecture is about. I want to show you one where it doesn't work. Okay. 3 plus 125. That's equal to 128. Let's just check they don't share any factors then. Well, that's 3. This is 5 cubed. And this, 128, is 2 to the power 7. Now this one is not like the first one I showed you. We've only got a few primes on the left, but we've got loads more on the right. So you've got more on the right than you do on the left. That's unusual. That's weird. So rather than not working, like I said earlier, it's the unusual example. These don't happen so often. So the technical way to say this is this. Times those primes together. So I'm going to do that. So 2 times 3 times 5 times 13 times 17, and that equals to 13,260. So it's a big number, and it's bigger than the right-hand side, which was this. That's what normally happens. Okay, so if you do this, you get a bigger number. Right? I want to show you this one that I said was unusual. If we do the same thing, 3 times 5 times 2, that's equal to 30, and that's smaller than 128. So that's the difference. So this is unusual. This is much smaller than the right-hand side. This number, which when you multiply the primes together, is called the radical of ABC. It's called the radical because it is well wicked. The ABC conjecture is the radical, which I've told you how to work that out, that's this. The radical of ABC is bigger than the right-hand side. I said that was C. Right, that's what you get normally. In fact, the conjecture is more than that. It talks about the powers of that too. But there are exceptions, and these are the exceptions. When k equals 1, that's the power is 1. There are infinitely many exceptions, just like the one I've just shown you there. Infinitely many. Even though I said these were the rare ones, the unusual ones, there are infinitely many of them. But if you take a power bigger than 1, even if it's only a little bit bigger, even if it's like a power of 1.00001. Tiny, tiny little bit bigger. If it's a bigger than 1, then you get finite. Finitely many exceptions. And this is a little bit surprising because, yes, if it's just a little bit bigger than 1, you get finitely many exceptions. You could count them off. You could write them down. You could say, here are all the exceptions for this power. And that's unusual. That's unexpected. Now, this is the conjecture. It's very abstract. It's very pure. This was made in the 80s, this conjecture. But if this can be proven, what it's going to do is it's going to prove a whole bunch of other stuff at a stroke. And that's why it's big news. Originally, they thought that Fermat's last theorem, which I talked about being solved in the 90s, they thought that this was the way to solve it. Because there is a way that if you can solve this, you can solve a version of Fermat's last theorem. It didn't turn out that way because Fermat's last theorem was solved first. I heard of it, I think, before it went round the nerdy blogs, and I thought, well, we could talk about it on Numberphile, but then it's still not been checked. So maybe we shouldn't talk about it on Numberphile. But then when all the blogs started going mad about it, I thought, someone might ask us